we continue with our discussion, and now I just want to briefly discuss one other important topic, which is probability distributions in R and how you can simulate observations from a probability distribution. And secondly, you can use this to solve some of the problems you do in probability theory. Okay, so I'll use an example, which is that let me assume that I have X, and X is normally distributed with mean 200, variance 10. I want to find the probability that X is what? Less than 95. Okay. Now, so this is normal distribution. And you see, in R, there are several distributions. So for example, for a normal distribution, I can talk about norm like this. And you see the health files for this are norm. So it's a normal distribution. You have density, you have distribution function, you have the quantile function and random generation from a normal distribution. It needs a mean and it needs a standard deviation. So this one is when you want to find density. So what is the density? Area under the curve and so forth. So for normal, this P is more or less like a cumulative distribution, and it can be survival function. If I set my lower dot tail to be false, it becomes a survival function. Now the Q is quantiles, and that is what we've been using for our test of hypothesis, where you read from the X. You want your test statistics, so you read from tables. So that is the quantiles. And R is for random number generation. Okay, so I want to simulate observations from a normal distribution. So what do? I will use random number, just like you will sample using sample in R. Okay. Now, so what do? I want to solve this problem. There are two ways I can convert this to what? A standard norm, or I can do it straight away. Now, because this is P, I will need P, right? Because this is compute the CDF, and you see my quantile here is what is my quantile is this one. So I have my distribution, then I want to find the probability that S lies um, below 195. So my KO is 195. The mean is from the distribution mu is 200. Standard deviation is square root of 10. And lower the tail is true. If lower the tail is true, it means it is finding from infinity to what? That 195. Okay. That's why I was saying that if you, and this is equal to what? 0.059. Now 569. If I want the survival function, which is 1 minus f, right? This CDF is what we usually will say what? F of x. F of x. So this is more or less um, f of 195. You know. Now here, I am looking at 1 minus f, the other tail. Okay. So if I want to do this thing, I can use the same thing. And then instead of this, I'll this to be false, which means you are looking at, and you should be able to tell me the answer because it's 1 minus that straight away. Okay. And that's it. 0.9542. So that's how you compute some of these things. Okay. Now, generating observations. Generating observations. Um, so if I know that a certain phenomenon follows normal 200 and variance 10, then I can generate observations from this distribution. So my S, let's say my sample data, I'm going to say R norm, okay, and then my N, what is my sample size? Maybe I need 100 of them. My mean is equal to maybe 200, and then my standard deviation is equal to what? SQRT of what? 10. Okay. Now, so I can do this and run. Now, one way to look at this is to plot a histogram of the data to see what we will get. There it is. So this is a histogram, and look at it. Histogram of S data is, you see, it's the mean is around 200 and so forth. So you can superimpose your density. So plot, um, no, lines, sorry, lines, okay, density, as you did in one of your assignments. And this is what some of you were experiencing. And it's good I did this because you see the density is way down there. The reason is that this is a frequency density. So I can't superimpose a density curve on it. If I want to do so, then it means I must now change my frequency to be false, right? To be false. And that one I'm going to get, and then I can lines like that and so forth. So this is a superimposition of my density curve. And the peak is around 200 and so forth. So that's how you generate observation. Let's look at other example, like this is from normal distribution, normal distribution. Um, let's look at exponential. So exponential, you are looking at RSP. So if you go to the help files, you see D. So each of them will have D for density, P for cumulative distribution or distribution function, Q for quanta, and R for random number generation. So if I want to generate observations, just RF and then the rate. Okay. So E data, exponential data, I'm going to do RS. Maybe sample size is equal to maybe 50. And then rate. Remember, this rate is your lambda, right? And your mean is what? 1 over lambda. Okay, so rate is equal to, let's say, 0.5. Then it means if I do hist of E data, there it is. And this looks like an exponential curve. If I have done the density, you'll see that it goes like that because the exponential curve is tilted to the right like that and so forth. So that's how you simulate observations from uh, observation. For the KO, we've done so much using our test. We've done QT, we have KO, chi, F, and so forth. So I I don't want to go into that again. So that's how you can simulate observations from um, a probability distribution. But I must stress that this is different from fitting a probability distribution. Okay? If you are fitting a probability distribution to a particular data, then that's different. This is just that the distribution is there. You are generating observations from it, or you are solving some, you want to find some probability concern. This is what I'm talking about. But if you are fitting a data to with a distribution, then you need something else. And for those that are interested, I will encourage you to look at FitDist. There's a package called um, Fit. So Mars has, there's FitDist. I think I have to download it. FitDist Plus, okay, which is a package. I don't have it here, but Mars has Fit. Let me check. Yeah. Okay. So Mars has Fit, FitDist R. So this will help you to fit an X, which is a data with some density function. And I'm not talking about this because some of you will need some estimation class before you'll be able to do this. And you do this later on. So beta, Cauchy, chi-square, exponential, gamma, and so forth. You can fit them using um, using such and there are even better ways of doing so using maximum likelihood and the other like fit dot this plus and then MLE functions to use maximum likelihood and so forth, which you can explore later on. Okay, so that's just my small discussion on fitting, sorry, on probability distributions in R.